This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more.
So today we're going to be talking about infinity and the cross ratio. So my subtitle for today, or the theme I want to sort of give this video, is sort of fixing something that we had with Mobius transformations. Now, everything we did last time it was correct and everything, but there's something that we can fix, and that involves our friend infinity. So recall from last time that a Mobius transformation is a linear fractional transformation of the following form. So AZ plus B over CZ plus D. Now remember, this was really close to being a bijection everywhere, right? But it wasn't quite a bijection everywhere. It's a bijection if we restrict the domain to C less minus D over C, and if we restrict the codomain to C less A over C. So this is so close to being a bijection everywhere, right? Well, we can make this a bijection everywhere if we take our complex numbers and we upgrade it just by a little bit. And that's what involves our friend infinity. Okay? So before we get to that, though, we have to talk about, well, what do we mean by infinity and how do we define infinite limits and everything? Because remember, infinity is not a number, right? It's a concept. It's a limit. We mean as big as possible. Well, we sort of run into an issue sort of fast. So let's think back to calculus for a second. Okay. So in calculus, if you want to be really precise about infinite limits, we have the following. So we say that the limit as x approaches a of f of x equals infinity if and only if, so this is the precise definition, if and only if for every m greater than 0, so this is replacing epsilon, if and only if for every m greater than 0 there is a delta such that if x minus a is less than delta, then f of x is greater than m. Okay. So what this is saying is that for any positive number m, okay, we can always find a delta such that if the distance between x and a is less than delta, then our function outputs are bigger than m. The idea being that we can make our function as big as possible. And if we can do that, that means it's going to infinity, right? Because infinity is as big as possible. Well, there's sort of a downside with this part right here. Okay? In real numbers, we can always compare two numbers as such. For instance, if I give you the two numbers 10 and 4, you could tell me right away which one's bigger than the other, right? You can say, well, 10 is bigger than 4. But if we take two complex numbers, let's say 1 plus I and let's say 3 minus 2I, which one's bigger? Okay? And that's actually a really loaded question. We can't just say right off the bat that this one's bigger than this, or maybe it's this way. I don't know. Okay, we can't really do that really easily like we could with real numbers. However, we can compare, instead of the complex numbers themselves, we can compare their lengths. So modulus, or length, gives us a way of comparing two complex numbers. So in this case, I believe we're going to have this true. If we compare their lengths, we would say that 1 plus I is less than 3 minus 2I when we think about complex numbers in terms of their lengths. Okay. So this is how we're going to have to compare complex numbers. We compare complex numbers through their modulus. Now remember, modulus is a positive number, right? It's a or a non-negative number. It's a length, right? So when we're talking about infinity in complex sense, we only have one infinity. We don't have negative infinity like we had back in calculus. So there's one big difference. We only have positive infinity because when we're talking about things blowing up, we're talking about things blowing up in length, okay? And that's a positive quantity. So we actually don't have this in complex land. And additionally, when we start to talk about limits, you're going to see this quantity a lot as well. So we wouldn't say f of z is greater than m. we have to upgrade this a little bit and say that the magnitude or the modulus or length is greater than m. Okay, so there's going to be a little bit of a difference in that as well. Okay, so let's formalize this though. All right, so let's suppose that we have a complex function from g to c. Okay, we say the following. So we say that the limit as z approaches z naught of f of z is infinity. This means that for every m greater than 0, so similar to calculus case, we can find a delta so that for all z and g with the distance between z and z naught less than delta, we have that the modulus or the length of the output is bigger than m. So this is the same idea as we were discussing earlier with calculus, or in calculus, and with real valued functions. When we say that a function has a limit of infinity, we mean that we can make that function as big as possible. And in a complex sense, we're talking about modulus. We can make the length of our outputs as big as we want. Okay, and that's what we mean by blowing up. Okay. Now, again, notice we don't have a negative infinity, right? We only have a positive infinity because we're talking about modulus now. We're not talking about real numbers, and real numbers can go to negative infinity. Complex numbers can't do that. At least not in the sense we're going with in this class. Okay. B. So we say that the limit as z approaches infinity, so again, here we're imagining the modulus of z getting bigger and bigger and bigger. So the limit as z approaches infinity of f of z equals L means that for every epsilon greater than 0, we can find an n, so that if the modulus of z is bigger than n, then the distance between our function and L is less than epsilon, or the modulus of f of z minus L is less than epsilon. Okay. And then finally C, we say that the limit as z approaches infinity of f of z equals infinity means that for every m greater than 0, there's an n greater than 0 such that if the length of z is bigger than n, then the length of its output is bigger than m. So again, same idea there. If the length of our inputs get really, really big, then the length of our outputs get really, really big as well. Okay? So similar ideas from calculus, except again, I want you to just think about this in terms of now modulus. This is how we compare complex numbers. We're comparing them through their lengths. Okay, not just the numbers themselves. And so we get something kind of cool, right? Again, we have an infinity, but we don't have a minus infinity because we're thinking about modulus here. Actually, let's not put that because we don't actually have the length of infinity. That's kind of a weird thing. Okay. Now here's an example that might blow your minds. The limit as z approaches 0 of 1 over z. Okay. Now you always hear me talk about Thanos snapping, right? And usually what I mean by that, at least in terms of calculus, is the following. So if we talk about the real valued function f of x equal to 1 over x, okay, this actually has no limit at 0, meaning the limit as x approaches 0 of f of x does not exist. Okay, and you kind of see that if you look at its graph, right? So what is the graph of 1 over x? It kind of looks like this, right? Okay. Now what happens when we approach 0? Well, if we approach 0 from the right, our function shoots off to positive infinity. Whereas if we approach it from the left, our function shoots off to negative infinity. And in calculus, infinity is not minus infinity, right? So we say that literally our function sort of blows up. It doesn't go to one infinity, it goes sort of in two different infinities in two different directions. So we would say the limit does not exist. Okay. Well, in complex land, we actually have a limit here. The limit as z approaches 0 of 1 over z actually is infinity. And one of the reasons for that is, again, we're not thinking about complex numbers as positive or negative because we don't have those meanings. We're thinking about them in terms of their length, their modulus. Okay? In any case, let's go ahead and prove this. So proof. Not prove, proof. All right, so how do we prove this? Well, let's go ahead and let m be greater than 0. Okay? And we want to find a delta greater than 0 such that if z minus 0 is less than delta, then f of z is bigger than m. Okay? Now I already did all the scratch work before. The delta we're looking for is actually just 1 over m. Let delta be 1 over m. Okay? So if z minus 0 is less than 1 over m, then we get the following. Okay, so then, well, this means that the modulus of z is less than 1 over m. Okay, hopefully everyone agrees that z minus 0 is z. And now if we would take the reciprocal of both sides, we're going to get 1 over z is greater than m, which is exactly what we want here. Oops, trying to draw an arrow there. All right, let's pretend like that's an arrow. In any case, we get exactly what we want. So what we just proved, everyone, is that the limit as z approaches 0 of 1 over z is infinity. So in a way, we can actually divide by 0 in complex land, although we have to be careful about that. Not quite yet. We have to formalize that, but we're getting there. That's sort of the punchline. Okay, another example, going back to our Mobius transformations, if you take the limit of a Mobius transformation as z approaches infinity, you actually just get a over c. Okay, now we're not going to prove that. You should try proving that on your own. But one way you can think about it, kind of going back to pre-calculus, think about the horizontal asymptote test. Horizontal asymptote test. If you guys remember from the horizontal asymptote test in pre-calculus, okay, calculus, there we go. The horizontal asymptote test said, well, if you have a rational function, f of x over g of x, okay, if the degree of the top equals the degree of the bottom, okay, then the limit of f over g as x approaches infinity was just the quotient of the leading coefficients. Leading over leading. So for instance, let's say we had 2x plus 3 over 4x plus 9, and we took the limit as that goes to infinity. Well, the degree of the top is 1, the degree of the bottom is 1, and so the limit would be 2 over 4, the quotient of the leading coefficients there. Okay. We have the same kind of idea going on with complex land here. Okay, so we have a over c in this case. We have degree 1 over degree 1, so we get a over c. Now, I'm not saying the horizontal asymptote test extends, but you can kind of think about it that way. But what I urge you to do, though, is try to prove this using the limit definition. But in any case, we do get that the limit as z approaches infinity is a over c. Okay. So let's actually improve our complex numbers a little bit. So again, I just want to stress infinity is not a number, first of all. Okay? Infinity is it's a concept, it's a limit. So whenever we're talking about infinity, we secretly have limits in the background. Okay? Just like we had back in calculus. Remember, in calculus, infinity was not a number. Even though sometimes maybe it was treated as a number, it's not. It's a limit. Okay? So be careful about that. But in any case, okay, we can sort of extend, and by sort of I mean we will be extending, we can extend the complex numbers by adding infinity, okay? And this extension is written as c hat, okay, with a little cap on it, that's a hat, okay? And so c hat is equal to c union infinity, okay? So we're taking the complex numbers and we're adding this placeholder infinity. And again, remember infinity, not a number, but it's sort of it's a limit. Okay. Now this extension is usually called CP1 or the Riemann sphere. Now it might be strange to think about this as a sphere, but this is kind of what's going on. If you want to picture this, remember the complex numbers themselves, it's a plane, right? So think about the complex numbers as a piece of paper. Okay. And what we're doing with C hat here, or the Riemann sphere or CP1, we're basically taking this piece of paper and we're folding it into a ball. Okay, so imagine taking a piece of paper and then trying to fold it into a ball, but notice you're always going to have a hole. Okay, and so what this infinity is sort of serving as is sort of filling in the hole there. Okay, so if we think about the complex plane, we wrap it up into a ball, we have some hole at, let's say, the North Pole, and so infinity is filling that hole. Okay, so that's why you can think about this extension C hat here as sort of a sphere. It's an actual sphere. It's like taking the complex plane, wrap it up into a ball. You're going to have some kind of hole at the top, fill in that hole with infinity, and boom, you got yourself a complete sphere. Okay? So in any case, that's why we call it the Riemann sphere as well. Again, I want to stress, whenever we're talking about infinity, we might not write it, but you always have to think about infinity as a limit. Okay, infinity is not a number, it's a limit. Okay. Now it turns out when we do this extension, so when we take C and we add infinity, we get a lot of nice properties. And some of these might seem reasonable, and some of them hopefully sort of make your brain explode a little bit. So in any case, definition. So the extended complex plane, C hat, is just taking C and we add infinity like we just discussed. Okay. So for any complex number, we have the following. Okay. So again, we're in the setting, we're in C hat here. So if you ever take a complex number and add infinity to it, you always get infinity. Okay, so infinity plus A is equal to A plus infinity, which is infinity. If A does not equal 0, then infinity times A equals A times infinity is equal to infinity. So any complex number times infinity is actually equal to infinity. Infinity times infinity is equal to infinity. Okay, infinity times infinity equals infinity. Now we get some really, really cool stuff. Okay, so part D here, this probably is not too unexpected, but if you take any complex number and divide it by infinity, you get 0. Okay, so if you take some number and divide it by something really, really big, you get 0, right? It's the same idea there. Now here's the mind melting here. So if A is not 0, then if you take A and divide it by 0, you actually get infinity now. So we can divide by 0 in C hat. This is supposed to be an explosion. Okay. So we can actually divide by 0 in the extended complex plane. And if we divide by 0, we get infinity, provided that we're not doing 0 over 0. 0 over 0 is, again, it's a crazy case that you have to be very, very careful with. So in any case, when we take the complex plane and we extend it with infinity, again, remember infinity, it's sort of a placeholder, it's not a number, we get these following properties here. Again, a lot of these you should sort of expect. Your intuition from calculus would serve you well here, except maybe for this last one. So now we can divide by 0, but we can only divide by 0 in C hat. Not in C, but in C hat. Okay, so any calculation that's not in this proposition needs to be investigated more carefully. Hopefully you noticed that infinity plus infinity was not on our list, right? And the reason for that is it's not defined. Sometimes it can be 0, sometimes it can be infinity. Sometimes it could be something else. It just sort of depends on the scenario that you're dealing with. So for instance, let me give you an example. If you took z plus z, okay, and you let z go to infinity, hopefully you will agree that this will go to infinity as z goes to infinity. Okay. However, if you took z plus minus z, okay, technically both of these go to infinity as z goes to infinity. And remember, this might seem really weird over here on the right. You might be like, wait, it's negative infinity. Remember, we don't have a negative infinity in complex land because we're always talking about modulus, right? So technically minus z would go to positive infinity. Okay. However, if you took the limit of z plus minus z as z goes to infinity, you actually get 0. Okay. So in any case, because of instances like this, you can't actually define infinity plus infinity. So whenever you have a situation that's like that, where it's infinity plus infinity, you have to be really, really careful about it. Other things you have to worry about, 0 over 0, you gotta investigate that a little bit more carefully as well. Okay. Another note, Mobius transformations, going back to those, like I said in the beginning of the video, remember that's sort of our theme here, they can sort of be upgraded. Okay, so our inversion, 1 over z, can now be defined at 0, because now we can actually divide by 0, and we get an output of infinity. Okay, and similarly, if we plug in infinity into this, okay, we get the number 0. So our inversion now is a bijection on all of the extended complex plane. So it is a bijection everywhere if you're working in C hat. F of z equal to z plus b is now defined at infinity, and it's still a bijection. It was a bijection to begin with, but it's now a bijection in all of C hat. Okay. And then our dilation can now be defined at infinity and is a bijection if we think about the extended complex plane as well. So basically what this is saying is the following. Okay, so we can take our Mobius transformations, and if we work in the extended complex plane, we get a bijection, and it's a bijection everywhere. We don't have to chop off anything. Okay, so corollary 3.8, suppose we have a Mobius transformation and suppose C is not equal to 0, then the Mobius transformation can be defined as follows. So as long as you're not plugging in minus d over c or infinity, then the Mobius transformation is exactly what it was in the previous video, az plus b over cz plus d. If you're plugging in minus d over c, which remember that was one of our plot holes in the last video, you get infinity now. And then if you plug in infinity, you get the number a over c. Okay, so now this takes our Mobius transformation, it upgrades it a little bit, and now it's actually a bijection on the entire extended complex plane. Kind of gnarly, so we've sort of upgraded our Mobius transformation a little bit. All right, so we're going to end this video with something called the cross ratio and its connection with the Mobius transformation. So let me give you kind of like a setting here, or like kind of what's going on. So let's suppose that some person walks up to you on the street and says, hey, I have a Mobius transformation that sends Z1 to, let's say, W1, Z2 to W2, and Z3 to W3. This would be a very weird conversation, but let's just suppose that it's happening. Okay. Now, he doesn't tell you, or they don't tell you, what the actual Mobius transformation is. But what's really cool about Mobius transformations, if you know this, you can actually say, well, I know that your Mobius transformation has to look like, let's say, like this. Maybe 2z plus 3 over iz minus 9. I don't know, something like that. But in any case, given this information, what we can do is we can actually identify what our Mobius transformation actually looks like. Okay, now I'm not saying it's always going to be this right here, by the way. This is just an example. But suppose we know this information, we can actually figure out what our Mobius transformation looks like, and that involves something called the cross ratio. Okay, so what is the cross ratio? So let z, z1, z2, and z3 be any 4 points in the extended complex plane. z1, z2, and z3, these are fixed. Remember, this is the information that we sort of know beforehand. Z here, this is our independent variable. Okay. So given these 4 points in the extended complex plane, then we define their cross ratio as follows. Okay, so it's kind of weird, but this is actually a function, and the notation we have here for this function is this bracket here. Okay, so instead of saying f of z, we write bracket z, z1, z2, z3. So in any case, bracket z, z1, z2, z3 is defined to be this sort of quotient or factored rational expression here. Z minus Z1 times Z2 minus Z3 all over Z minus Z3 times Z2 minus Z1. Okay. So a couple of comments. First of all, we have some implicit definitions embedded into this. So first of all, if we plug in Z3 into this function or this cross ratio, notice that we're going to be dividing by 0. And remember, in the extended complex plane, that means you're going to get infinity. Okay. Additionally, if one of z, z1, z2, or z3 is infinity, then the two terms in our cross ratio are going to cancel, and we actually get a pretty nice expression in the end, which your book gave you a pretty nice example of. So if like the first core, or if the z1 was infinity, this is what we would end up with. Okay, pretty cool. Anyway, so what does this have to do with our function? So we have a couple of propositions, or a couple of things we need to talk about. So first, let f be a function from the extended complex plane to the extended complex plane defined by our cross ratio. So remember, think about these as functions. Then we actually have that the cross ratio is in fact a Mobius transformation that satisfies the following. So f of z1 is equal to 0, f of z2 is equal to 1, and f of z3 is equal to infinity. Okay. Now to see this, let me kind of walk you through it a little bit. So first of all, remember our cross ratio is defined to be the following. Oops. Okay, so this is z minus z1 times z2 minus z3 all over z minus z3, z2 minus z1. Okay, so first of all, what I recommend you do, we don't have too much time in this video, if you actually factor everything, you can actually see that this can be written as az plus b over cz plus d for some complex numbers a, b, c, and d. So basically, if you just factor, or FOIL, I should say, you can actually take your cross ratio and put it into this form so you know that you have a Mobius transformation on your hands. Additionally, let's just kind of walk through the computations here. So if you plug in Z1, what's going to happen, notice this first term here is going to be 0. Okay, so then your output's going to be 0. If you plug in Z2, well, you're going to get Z2 minus Z1, Z2 minus Z3, Z2 minus Z3, and Z2 minus Z1. And notice we get a bunch of cancellations. These cancel out like that. These cancel out like that, and all we're left with is 1. And finally, like we said earlier, if you plug in Z3 into this function, you're going to be dividing by 0, and remember in the extended complex plane, that's infinity. Okay, so that's the first part of this proposition. The Mobius, the cross ratio actually gives you a sort of factored Mobius transformation that does this to Z1, Z2, and Z3. Okay. Now here's where it kind of gets pretty interesting. We'll need this fact in a little bit. So suppose G is a Mobius transformation with the same properties. So suppose that this G, another Mobius transformation, sends Z1 to 0, Z2 to 1, and Z3 to infinity. Then F and G actually are the same function. Okay, so what this is what we call in math a uniqueness theorem. Okay. Basically, it's saying that the cross ratio here is the only Mobius transformation that's going to send Z1 to Z2, Z1 to 0, Z2 to 1, and Z3 to infinity. And so what this is implicitly saying, well, if you had another one, well, it had to be the same function to begin with. So let's prove that, though. So that is a little bit tricky. So proof, let me change colors here. Let's go green. All right, proof. Okay. So to prove that it's unique, we actually have to be a little bit tricky with how we do things here. So the first thing we're going to do, all right, so let me go ahead and switch to green. So let's go ahead and prove that uniqueness bit. So let's suppose G is another Mobius transformation. Okay, with G of Z1 equal to 0, F of Z2, G of Z2 equal to 1, and G of Z3 equal to infinity. Okay, so our goal is to show that actually G is equal to F. Now, how are we going to prove this? Well, we're going to actually be a little bit tricky about it. Okay, so to prove that G equals F, what we're going to prove instead is prove that if we take G and compose it with F inverse, then we actually get the identity function, Z. Okay. Now, if we can show this really quick, let me just show you why is this enough to prove that G equals F. Well, if we can show this line, all you have to do is compose on the right with F. Okay, and then these cancel out now, and you get G on the left, and then what is Z composed with F? That's just going to be F again, and boom, you do get G is equal to F. Okay, so this is what we're going to aim to prove, though, is that G composed with F inverse is actually equal to Z. All right, so let's go ahead and prove that. Well, first of all, we need a couple of facts. One, so F inverse, since F is a Mobius transformation, F inverse is also a Mobius transformation. Okay, remember that was from last video. If you take the inverse of a Mobius transformation, remember it has that same form as a Mobius transformation, so it itself is a Mobius transformation. And two, whenever you compose Mobius transformations, you get another Mobius transformation. So G composed with F inverse is also Mobius. Also Mobius. Okay, now why we need this right here is now we can say, well, G composed with F inverse, we know that this has to look like AZ plus B over CZ plus D. Then our goal is to show, well, C is 0, and we want to show A is 1, and then we want to show that B is 0 and D is 1 as well. Okay. We'll get to that, but in any case, that's sort of where we're heading with this. We want to show somehow that this is just equal to z in the end. I'll put a little question mark next to this. All right, so how do we show this? Well, we're going to actually just plug in our given information. So what happens if I plug 0 into this? Okay, well, if I plug 0 into this composition, what do we get? We get g of f inverse is 0. Oops. And I just wrote the same exact thing. I meant to write it like this. G of, there we go, f inverse is 0. And now remember, f satisfies the following. Remember, f of z1 is 0, f of z2 is 1, and f of z3 is infinity, right? Well, this means if you take inverses of all these equations, you're going to get that z1 is equal to f inverse of 0, z2 is f inverse of 1, and z3 is f inverse of infinity. Okay, so what is f inverse of 0? That's equal to z1. Okay, and what is g of z1 by our assumption? G of z1 is 0. Okay, all right. So what did we get after this? Well, let's think about this. We know that our Mobius transformation looks like this as well, right? And if we plug 0 into this, we get a times 0 plus b over c times 0 plus d. We get b over d on this side, but it has to also be equal to this right here. Okay, so we know that 0 is actually equal to b over d. Okay. Now, if b over d is 0, well, multiply both sides by d, we get b is equal to 0 as well. Okay, so really our Mobius transformation here doesn't actually include a b now. We know b is 0. So our Mobius transformation has to look like that. Okay. All right, next step. Let's plug in 1. Okay, so what is g of f inverse of 1? Okay, well, this is going to be g of f inverse of 1. Okay, now what is f inverse of 1? If we look over here, we know that that's z2. And what is g of z2? By our assumption here, g of z2 is 1. Okay, so if we plug 1 into our g composed with f inverse, we know that we get the number 1 out. On the other hand, if we plug it into our expression for g composed with f inverse, we get a over c plus d, and we know that's equal to 1, right? So what does this mean? This means that a equals c plus d. Okay. So now more on that in a second. We'll come back to that, but keep that in the back of your heads. A is equal to c plus d. Okay. Not too much we can do with that yet, but we'll get to it. All right, lastly, with our last piece of information here, let's plug in infinity. Okay, so g composed with f inverse of infinity. This is g of f inverse of infinity. Now, by our assumption here, what is f inverse of infinity? That's z3, so this is g of z3. And what is g of z3? G of z3 is also infinity. Okay. On the other hand, what do we know? Let me erase this part. If we plug infinity into this expression here, what do we get? We're just going to get a over c. Okay, so if a over c is equal to infinity, which is the right-hand side over here, that means that, just think about how do we blow up? Well, we blow up when we divide by 0. So this means that c has to be equal to 0. Okay, and now finally, when we take that information, remember a was equal to c plus d, we can put that into here, so we know that a actually has to be equal to d. Okay, so adding all this together, now we know c is 0, a is equal to d. Okay, what does our Mobius transformation here become? All right, so c is 0, this goes away. And we know that a equals d, so this becomes az over d, but since a is equal to d, this just becomes z, and that's exactly what we wanted to show. Boom. Sorry, it's hard working with one slide, but in any case, we know now that this cross ratio is actually the unique Mobius transformation that sends z1 to 0, z2 to 1, and z3 equal to infinity. Okay. All right, so the last thing we're going to talk about again is answering that question, because remember, we're still under that scenario. Some guy randomly walks up to you and says, hey, I have a Mobius transformation that sends Z1 to W1, Z2 to W2, and Z3 to W3. And again, I said if you know that information, you should be able to figure out exactly what the Mobius transformation looks like. So corollary 3.13 actually tells us that. So again, suppose Z1, Z2, and Z3 are distinct points in the extended complex plane. And let's say W1, W2, and W3 are also 3 distinct points in the extended complex plane. Then there exists a unique Mobius transformation that sends Z1 to W1, Z2 to W2, and Z3 to W3. Okay. Now that's the corollary, and it actually hasn't answered our question yet, but if we look at the proof of the corollary, it actually tells us how to do that. So if we want to figure out exactly what this function is, h, that sends Z1 to W1, Z2 to W2, Z2 to W3, if you look at the proof, all you have to do is take G inverse of F, where G is this cross ratio here, and F is this cross ratio here. Okay, so if you take the inverse of this and compose it with F, then you actually get the function that we're sort of looking for in our scenario.